Hi, I'm Senan and let's look at AVL trees. An AVL tree is a self-balancing binary search tree. That's important, where the difference of heights between the left and right subtrees is at most 1. We'll look at this in a later part of the video, but what's important here is the self-balancing and the binary search tree property. AV in AVL stands for Adelson-Welsky and L stands for Landis. So these two actually wrote a paper in 1962 in Russian. And if you translate this title, this would say an algorithm for the organization of information. What is the plan for this video? So I'll introduce AVL and we'll see how to search an element in an AVL tree. Then we'll see rotations, which is the LL, LR, RL and RR imbalances and how to rotate and make corrections. Then we look at inserting an element in an AVL tree. And this we are actually going to build an AVL tree. And after that, we'll have a separate video for deleting an element. There are 4 ways in which you delete an element in an BST. Using those, we have some other modifications in that algorithm itself to perform deletion in an AVL tree. And finally, I may or may not make a video on additional information which are important with respect to an AVL tree, but you don't necessarily need to watch that. These 4 topics are actually important. So whenever you talk about an AVL tree, you talk something known as the balance factor, which is height of left subtree minus height of right subtree. Let's start with this root node 4. The height of left subtree is 2, height of right subtree is 3. Therefore, the balance factor is 2 minus 3, which is equal to minus 1. Similarly, the balance factor here is 1 minus 1, 0. For this, there is no left child or right child. Therefore, the height of left subtree is 0, height of right subtree is 0. Similarly here, and in this case, the left subtree has a height of 1. There is no right subtree, so 1 minus 0, which is equal to 1. But if you look at this node 5, what you see is there is no left subtree, but the height of right subtree is actually 2. So balance factor is minus 2. For all nodes n, if balance factor of n belongs in this range, minus 1, 0 and 1, then it is an AVL tree given it is already a binary search tree. So in this case, this is a binary search tree, but if you look at this node, the balance factor is minus 2, which is not in this range. So therefore, this is not an AVL tree. Since this AVL tree is also a binary search tree, in-order traversal is a sorted list of numbers, and the height of the tree would be of order log n. As AVL tree is a self-balancing binary search trees, we need a way to balance those, and we do the balancing with something known as rotations, which is a topic for the next video. Let's look at some of the examples. In this case, it's a BST, as well as for all the nodes, the balance factor is within the range minus 1, 0 and 1. So this is an AVL tree. In this case, the same as the above, this is not an AVL tree because the balance factor for this is minus 2. If you look at this, you have the balance factor property satisfied, but it is not satisfying the binary search tree property, which is the elements to the right are actually greater than the node. So 0 should be greater than 4, which is not the case. And a null node is also an AVL tree because for checking the balance factors, you need to have a node. So this tree has 0 nodes. So the balance factor property holds vacuously. Now let's see how to search an element in an AVL tree. So this would be our node structure. The left subtree, the right subtree, the value, same as the BST, but we store an additional element of height. Now this height is used for calculating the balance factor, and that can be done in order one time because I can access the height of the left tree, I can access the height of the right subtree, and then I can just subtract them to get the balance factor for this node. Let's try to find 6 in this AVL tree. So starting with the root, 4 is not equal to 6. If 6 exists in this tree, it would be on the right. So I go and check the right subtree. Now 5 is not equal to 6. So again, 6 is greater than 5. So if 6 exists, it would be on the right subtree. Now I go to 7. Now 7 is not equal to 6 and 7 is greater than 6. So if 6 exists in this tree, it would be on the left side of 7. So I go and check the left subtree, but there is no subtree on the left. I can conclude that 6 is not in this AVL tree. This algorithm is exactly like searching in a binary search tree. Let's look at the pseudocode. This would return a boolean value, and for searching you take the root and a key value that you need to search. Now if root is null, you return false because there is no tree to search. If root's value is equal to key, you found your element. So in that case you return true. Otherwise what you do if root's value is less than the key, that means if the key is present, it would be on the right subtree. So you recursively call this search on the right subtree. Otherwise it would be on the left, so you search the left subtree. Now the time and space complexity would be order log n for both. And this is true because every time you search an element, the search space is actually reduced by half. That is why it's order log n. And since you're recursively calling these functions, it would take order log n as the stack space. But if you observe, this recursive call is in the end. So that means this is a tail recursion. So any good compiler would convert this into a iterative solution. It would have the same structure. And what you'll do is while root is not equal to null, you'll check if root's value is equal to key. In that case, you would return true. Otherwise, if root's value is less than key, that means if key exists, it would be on the right subtree. So you update the root to root's right child. Otherwise, you update the root to its left child. And if you're not able to find your element in this while loop, that means it does not exist. So you return false. Now the time complexity is same order log n because of the same reason, but we've optimized our space to order 1 because there is no recursion stack space involved. Now your task is to write the above code in the comment section in the language of your choice so that you know that you actually understand what I'm trying to teach. That's it, and I'll see you in the next video.